Okay.
Okay. I'll kick us off here. Hi, everyone. Welcome back to the ECS and Cloud Feedback Virtual Symposium. This is our 21st meeting. And we have a really great bunch of talks for you today. But before we get to them, let me just remind you about some logistical things. So we're going to have 3 12-minute talks. There'll be some time for a few questions after each one, and then if we have time for it, we'll have a short sort of general Q&A at the end. You should all be muted right now, so if you have any questions or comments for the speakers, just type them into the chat at any time, or if you'd rather ask them directly, raise your hand and then we'll unmute you during the question and answer sessions. So we're always on the lookout for speakers. If you want to give a talk, please reach out to anyone on the executive committee. You can find our contact information, as well as a whole lot more, including videos of past talks, how to sign up for the mailing list at our website, which is here. And so with all that, we're going to move on to the first talk, which is going to be from Andrea Dittus. Andrea, do you want to start to set up your slides?
Yeah, sounds good.
Dr. Dittus is a research scientist at the University of Reading, and she'll be talking today about the regional impact of climate stabilization at different global warming levels.
Okay, should I make a start?
Go ahead, take it away.
Great. Thank you, Jonah, for the introduction, and thank you to all the organizers for the invitation. I'm really happy to be talking to you guys today. So yeah, as Jonah mentioned, I'll be talking about the regional impacts of climate stabilization at different global warming levels. So I realize it's a little bit different to what you usually have here on this symposium, but I hope will be of interest regardless. So I just want to thank my co-authors, Ed Hawkins, Matt Collins, and David Sexton from the University of Reading, Exeter, and the Met Office, respectively. So just a very brief introduction. So since the Paris Agreement in 2015, there's been a lot more demand for information of climate projections to be provided at various global warming levels, in particular the 1.5 and 2 degree global warming level, but also higher warming levels, such as, let's say, 4 degrees global warming. And this is an example from the IPCC 6 assessment report, Summary for Policymakers, showing projected climate change for temperature and precipitation at these specific global warming levels. So typically, a lot of the time, these projections at warming levels are provided by extracting information from transient scenario simulations, so from scenario MIP, for example. But the implication of the Paris Agreement is really to stay below those warming levels of 1.5 or 2 degrees in the long term. And so we have to think about what the change would look like if we stabilize at those target global warming levels. And so that's what I'll be focusing on in my talk today. And so, as I've mentioned, there's different types, different methodologies to extract information about global warming levels. So typically, we often do this with transient simulations, for example, from the scenario MIP experiments. But then there's also different ways to look at this. So one example I'll talk about today is about fixed forcing experiments, where we branch off some scenario MIP simulations at various levels and run forward for a number of years. So these are fixed forcing or fixed concentration experiments, and I'll say a little bit more about that in a second. And this is quite similar an approach to equilibrium or equilibrium type simulations. So for example, the long run MIP simulations, which are run for thousands of years. And so while these are not directly targeting global warming levels, that's a similar type of approach to fixed forcing simulations. And so under fixed concentrations, there is typically committed long-term warming past fixing the concentrations due to a reduction in the ocean heat uptake efficiency. And that's shown here. I'll go into this figure into more detail on the next slide, so I won't talk too much about it, but you can see that these are our UK SM1 fixed concentration simulations and the rapid warming SSP 3700 transient simulation shown here for comparison. And you can see that in these 500-year-long simulations, there is still some ongoing warming that continues over several centuries. And in contrast, we can also have zero emission type simulations where the carbon concentration can change. So there's an uptake in carbon dioxide from the land and the atmosphere, and so from the land and the ocean. Sorry, I meant to say. And so the atmospheric carbon dioxide concentration can decline over time, and that results in a stabilization of global temperatures in these types of zero emission simulations. Of course, that is model dependent, but by and large, the decrease in atmospheric concentration in atmospheric carbon dioxide compensate this reduction in the efficiency of ocean heat uptake. And so I've briefly talked about this approach, this fixed concentration approach, and for zero emissions, we have there are two different approaches that I'm aware of, but there might be more. So the zero emission commitment MIP has prescribed an experimental design where the emissions are set to zero at a given point, at a given level of cumulative CO2 emissions. And there's also a proposed experimental design that Andrew King proposed in a comment that I was involved in a couple of years ago. And these are similar types of zero emission experiments, but in contrast to ZECMIP, the target variable is the temperature level, so not all models will be branching off at the same point. So that's all I'll say about the zero emission experiments, but I just wanted to briefly mention them here. So the experiments we've done with UKSM1, as I've mentioned, they're fixed concentration runs, so they will have some ongoing warming, as you can see here. So we have 6 simulations that are run forward for 500 years. And while these aren't true net zero type experiments, for the reasons mentioned, they are still warming much more slowly than the high emissions scenario MIP simulations. So for example, here, SSP 370 on the left. And so what we can do is compare the patterns of change at given warming levels. So for example, here, the 3-degree level in a rapidly warming world and in a stabilized world, or a world that is warming much more slowly. And this is what you can see here on the right. What is shown here is the difference between the stable and the transient patterns of temperature change. So for the same global warming level, stable minus transient, so the stable simulations show much reduced warming over the land and the tropical and subtropical oceans, and much enhanced warming at the poles. So especially the Arctic, but also the Southern Ocean and Antarctic. And so we can use these types of simulations to answer the questions, how does a stable climate differ from a transient one? And as I've mentioned in the previous slide, we have much amplified warming in the stabilized simulations at the poles, and this can also be seen in the sea ice concentration. So this figure here is showing sea ice concentration at 1.5 degrees at the top and 2 degrees of warming at the bottom for transient on the left and stable in the middle, and stable minus transient being shown here on the right. And in the stabilized simulations, there is much reduced sea ice concentrations compared to a transient simulation. We can also see important differences in precipitation. So here I'm showing June, July, August precipitation, again for different warming levels, so 2 degrees, 3 degrees, and 4 degrees. For stable on the left, transient in the middle, and the difference on the right, so stable minus transient again. And so I won't be talking about all of these differences today, but what you can see here is that there are quite important regional differences. So for example, there are differences in the tropical Atlantic or over Europe. And for the next few slides, I'll be talking about the differences over Europe. So summer precipitation change over Europe. So here I'm showing in brown is the projected precipitation change from the SSP 370 simulation. So it's been quite well known for some time now that under a high emission scenario, there's strong drying in in different regions over Europe. So here I've split this into Northern Europe, Western Central Europe, Eastern Europe, and the Mediterranean. And so you can see a pretty strong precipitation decline in all of these regions. But if we look at the stabilization runs, we can see that this decline is reversed or stabilized, or a stabilization or reversal of these precipitation trends. So if we look at the Mediterranean, we can see a stabilization of precipitation at the level of branching off. But if we look at other regions, for example, Eastern Europe, we can actually see a recovery towards the baseline. So the baseline here is 1850 to 1900. So we can see a recovery towards the baseline, and perhaps even more strikingly for Northern Europe, we can see a wettening trend that continues over several centuries and goes above the baseline. So we have wetter conditions at the end of our stabilization runs than we did at the beginning of the historical period, 1850 to 1900. And on the right here, I'm showing the precipitation change as a function of global warming level. So the brown again is showing the SSP 370 transient simulation. And so you can see a precipitation decrease for each additional level of global warming. If we look at the stabilization runs, however, you can see a wettening for each additional level of warming. And what you can also see is that this is more dependent on the timescale from branching off from the scenario MIP simulations rather than the global warming levels. So a given precipitation change can be consistent with different warming levels. So that suggests that there's a dynamical mechanism at play, and one key candidate for that is the SST patterns. So this is something that I'm currently looking into, so it's work in progress, but based on the literature and the results we have so far, that seems like a key candidate to explain these regional precipitation differences. I've just reset my watch accidentally, Jonah. How am I going for time?
You're okay, a few more minutes.
Okay, great. So I'll just show 2 more slides on these runs and then I'll wrap up. So one other characteristics of these simulations is that we have 2 simulations that have exactly the same temperature evolution, which you can see here where the arrows are pointing at. But they are branched off from different SSPs. So one of those runs is branched off from SSP 370, and one of them is branched off from SSP 245. So they have the exact same global mean surface temperature trajectory, but have different atmospheric composition, with the SSP3 based run having higher anthropogenic aerosol and higher carbon dioxide levels. And there's also differences in the land surface cover. And so you can look at the difference between those 2 simulations. So here showing the SSP3 based run minus the SSP2 based run. And on the left here, you can see the difference in the aerosol optical depth pattern. So our SSP3 based simulations has higher overall anthropogenic aerosol emissions and a greater concentration of aerosol over Asia, for example. And this leads to regional differences in the temperature and sea level pressure patterns. So for example, you can see a very large regional warming over the North Atlantic, or I say very large, but a relatively large relative warming over the North Atlantic, Europe and Northern Asia. So that's quite a large difference. It's up to 1 degree Kelvin, so non-negligible difference. And there's also an important difference in the sea level pressure in the North Pacific. So an increase in North Pacific sea level pressure in the Aleutian Low region, and an associated temperature cooling pattern that projects onto the negative phase of the PDO, or a pattern that looks like the negative phase of the PDO. And in previous work, we found this North Pacific sea level pressure increase and cooling pattern in the North Pacific to be associated with an increase in aerosols. So that would seem consistent with that finding from previous work. And since it's not the main focus of the talk today, I won't talk much about this, but just if you're interested, we had a paper a couple of years ago looking at the role of aerosol forcing to explain this pattern of SSTs that is talked about a lot in this community from the 1980s to 2014. So yeah, if you're interested, please have a look, or happy to chat about it further offline. And so to wrap up or to summarize, the takeaway messages are that warming is reduced in stable climate simulations compared to transient climates in many land regions. And there are also large differences between transient and stable regional climates for the same global warming level in many regions that includes precipitation changes that can be opposite in sign in some regions. And so that is quite an important difference to consider. And finally, there's also some differences in regional patterns that can occur due to differences in atmospheric composition, so due to a difference in the balance of external forcings. And so, yeah, the final message, if you will, is that, my final conclusion is that regional impacts can be very different between stabilized and transient climate change projections. And so perhaps stabilized projections should be considered to help ensure that we are making robust adaptation decisions if we are serious with moving towards a net zero climate. And I'll stop there. Happy to take questions. Thank you.
Awesome. Thanks so much, Andrea. It was a great talk. Maybe could you leave your slides up?
Yep. I'll bring them back up.
So everyone, again, please either raise your hand or put questions in the chat. And trying to organize here. While people are thinking of questions, I want to ask Andrea, when you're showing the differences in warming between the stable climates and the transient climates, you focused on sea ice. But given the long timescales you were looking at, I was wondering if you've looked at changes in AMOC and ocean heat transport in the Atlantic.
Sorry, I was muted and I'm just going to share again. I just couldn't find the unmute button. Yeah, thank you for the question. So yes, I've had a quick look at the AMOC, but not in much detail yet, and even less at ocean heat transport. But it looks like so there is an initial decline in the AMOC in the scenario map simulations probably due to greenhouse gases, and that continues for the first 20 years of the runs. But after that, the AMOC seems to be strengthening again and recovering towards the level they were at before the decline, but it's perhaps not getting there fully, but there seems to be a recovery towards where it was before the decline, if that makes sense.
Cool, interesting. Thanks. Carsten has a question. Carsten, you want to unmute?
Andrea, really great stuff. It's actually one of those topics where I've been wondering for the longest time whether actually someone looked into it. So you did, it's, at least as far as I'm aware, the most like explicit attempt to quantify it. So really well done for that, because whenever and that's an issue, I guess, not only in Germany, but particularly here, if you guys followed the conversations, that drought has become a real deal. And whether or not that this is going to continue into like a non-transient future is an obvious question to ask. And we didn't have the answer. And for decision makers, while we will be in this transient scenario for the time being, it might actually play a role to know what comes after that. So well done for that. And one like short question in that regard would be, focusing on Europe again, is it just a thermodynamic response, especially the intuitive change in precipitation in an equilibrium scenario, or is it also dynamic? Did you look into that? Thanks.
Thanks for the question, and yeah, thanks, Carsten. Yeah, so just a quick note to say, I think there are some other papers looking at similar things, and I know other people are working on stabilization simulation. So there is a bit more work out there, but I agree that there's not a lot. But yeah, so I can't fully answer your question about the precipitation change, but I suspect it is dynamic, because you can have a warming level that is consistent with multiple precipitation levels or levels of precipitation change. So if it was purely thermodynamic, you'd expect that to be a global warming level to uniquely define a precipitation change, if you know what I mean. So I suspect it's mostly dynamic, but what the exact process is currently under investigation.
Okay, I mean, if I may, the very simple intuitive response in a transit scenario is that the land-ocean difference is much larger, obviously now, than it will be in the future. So there's much less moisture to be available over land to start with. So which would explain why it's drier now as opposed to later. So I could explain or see that that it works without a dynamic role, but dynamics is certainly not to be neglected. But yeah, thanks again.
Thanks, yeah.
Thanks, Andrea. Thanks, Carson. I think we should move on to Casey. But Andrea, I see there's already a question for you in the chat, so please keep an eye out there.
Okay, our next speaker will be Casey Wall. Dr. Wall is a postdoctoral researcher at the University of Oslo. He's working with Trude Storalpmo, and today he'll be talking about assessing the effective radiative forcing from aerosol cloud interactions over the global ocean.
Great. Thanks, Jonah, for the introduction, and thanks everyone for showing up today. I'm really excited to be here. I will be sharing some estimates of effective radiative forcing from aerosol cloud interactions that I've done in collaboration with Joel Norris, Anna Posner, Daniel McCoy, Isabel McCoy, and Nick Lutzko. The motivation for our work is, as many of you know, historical aerosol forcing is one of the key uncertainties in the evidence we have for estimating equilibrium climate sensitivity. So if we can reduce uncertainty in aerosol forcing, it can potentially give us more reliable estimates of ECS. And so in the work I'll show today, the goal is to take methods developed from the cloud feedback community, apply them to the problem of estimating historical aerosol forcing, and hopefully reduce uncertainty in that quantity. All the results I'll show today are about interactions between aerosols that can act as cloud condensation nuclei, or CCN, and low-level liquid clouds. So I'd like to begin by just talking through some of the proposed mechanisms from the literature that can govern these interactions. So first, if there are more CCN in the boundary layer, those CCN are ingested into clouds. That can cause more numerous but smaller droplets to form in the cloud, which can cause an instantaneous change in the cloud albedo, called the Toomey effect. The change in the droplet number and size distribution can then cause the cloud to adjust in other ways that can affect the liquid water path or cloud fraction. So for instance, if the cloud is not precipitating, more CCN can cause smaller droplets, which are more susceptible to evaporation. So the aerosol influence can increase evaporation and reduce liquid water path. If the clouds are precipitating, there's other adjustment mechanisms that can come into play, which are illustrated in this diagram on the bottom. So starting on the left of the diagram, if there's clean conditions, the cloud droplets are relatively large. They coalesce into raindrops quickly, and the precipitation creates cold pools that collide with each other and shape the cloud field, so it's more broken up horizontally. If more CCN are added to the boundary layer, so that's moving to the right on this diagram, the cloud droplets get smaller, the precipitation gets weaker, the cold pools get weaker or disappear, and as a result, the clouds become more horizontally extensive. And so this can have two effects on the cloud properties. First, more CCN can be associated with larger low cloud fraction. And second, more CCN can be associated with smaller liquid water path values averaged over the cloudy pixels. And the reason for the liquid water path relationship is that the thick, rainy cores of the clouds make up a smaller proportion of the cloud area in the polluted conditions on the right than they do in the clean conditions on the left. So all of these aerosol-driven cloud changes can then have an impact on the radiation budget. And the quantity of interest for climate is the effective radiative forcing from aerosol cloud interaction, or ERF-ACI for short. This is defined as the change in the top of atmosphere radiation flux from the Toomey effect and adjustments combined. And in our work, we're going to attempt to estimate this quantity. To estimate ERF-ACI, we use a framework called cloud controlling factor analysis, originally developed by Ryan Scott and Tim Myers. We use monthly gridded satellite cloud data from Ceres and MODIS, and we select for analysis the low cloud properties, where low clouds are defined as clouds with cloud top pressure larger than 680 hectopascal. We relate the cloud properties to local environmental predictor variables from MERA2 reanalysis. The predictor variables include 6 meteorological terms listed on the right, which together encapsulate all proposed mechanisms by which the large-scale meteorology influences marine low clouds. And also we have a 7th predictor, which is the logarithm of sulfate aerosol concentration at 910 hectopascal. And we focused on sulfate in our work because it's believed to dominate the anthropogenic influence on CCN. So from these data, we select ocean grid boxes between 55 degrees north and south, remove the seasonal cycle and long-term trend from all of the variables, and then average the anomalies over a 5 degree by 5 degree grid. And then for each grid box, we perform a multilinear regression analysis where the low cloud property anomalies C are regressed against anomalies of the 7 cloud controlling factors. And from this analysis, we get a regression coefficient that relates anomalies of low cloud property C to local sulfate anomalies, which is highlighted at the bottom of the slide. But also, since we're including all the meteorological terms in the regression model, effectively we're controlling for the meteorology and isolating the aerosol cloud relationship. So we'd like to use this analysis to eventually estimate ERF-ACI, but to start, we wanted to look at other cloud properties to look for evidence of the proposed aerosol cloud interaction mechanisms. So the map shown here shows relationships between cloud droplet effective radius and local sulfate anomalies. The blue colors indicate that larger sulfate concentrations are associated with smaller cloud droplets, and the stippling shows significant relationships. So this map here is showing some evidence for the Toomey effect. The next map below shows the relationship between liquid water path and local sulfate anomalies. Here, red colors show that larger sulfate concentration is associated with smaller liquid water path. And we see this relationship particularly in the stratocumulus regions. And then finally, the map on the bottom shows the relationship between low cloud fraction and local sulfate anomalies. Here, blue colors show that larger sulfate concentration is associated with larger low cloud fraction. We've also looked at proxies for precipitation occurrence and a proxy for the horizontal size of low clouds. And we've also checked robustness of the results using different cloud data sets. So the maps on the right are calculated with MODIS cloud observations. And on the left, these are the same maps, but calculated with the Ceres cloud retrievals. And we find consistent results there. So all of these results are consistent with the proposed mechanisms of aerosol cloud interaction that I started with, namely that larger sulfate concentration is associated with smaller cloud droplets, smaller liquid water path, and larger cloud fraction. So next we wanted to relate the cloud anomalies to the radiation budget. And we do this using the metric of the low cloud radiative effect, indicated with an R. And we have done the same regression analysis at every grid point, but to consolidate the results, we average the regression coefficients over 3 different geographical areas indicated in the map on the top. One is representing stratocumulus regions, another cumulus, and the third mid-latitude. And the regime average regression coefficients are shown in the bottom panel. So what we see from this analysis is that in all 3 regimes, when the sulfate concentration gets larger, The low clouds reflect more shortwave radiation to space. And the relationship is strongest in the stratocumulus regime and weakest in the cumulus regime. To test robustness, we've also done this analysis with 3 different estimates of cloud radiative effects. We use different cloud data sets, including Ceres and MODIS. We use different methods for calculating radiative kernels. And we use different filtering choices for partially cloud-covered pixels, which have uncertain retrievals. And in all cases, we found consistent results. So the fact that we get consistent estimates with different data sets and methods is giving us some confidence that we're seeing a robust physical signal here. So now we have some estimates relating cloud radiative effects to a sulfate concentration, but there's still an issue of causality that we need to look into before we can make estimates of aerosol forcing. And the reason for that is we know from a lot of previous literature that sulfate aerosols and liquid clouds are coupled with each other through two-way interactions. So when we're looking at natural variability, it's not always obvious if the aerosols are causing the clouds to change or vice versa, or both at the same time. And so this can potentially be problematic for making estimates of aerosol forcing. So to address this issue, we've looked at a couple test cases where we know there's a change in sulfur emissions, which has been causing a change in the clouds, and see how well our model can perform in these cases. So the first test case we looked at is in Eastern North America. The region we looked at is the box in the inset map on the bottom left of the figure. And what's shown in this graph on the left is a time series of sulfate anomalies averaged over the box, where the seasonal cycle has been removed, but the long-term trend is left in. So you can see a significant negative trend over the record, and this is caused by stronger emission controls on sulfur emissions in the eastern United States and North America. Furthermore, when we did our regression analysis, we removed the trend of all the variables prior to computing the regression coefficients. So information from this trend isn't used in the training of the regression model. So in this case, we used the test case to ask the following question. If we input trends in all the cloud controlling factors into the regression model, does the method predict correctly the trend in cloud radiative effects over this period? And the result of that calculation is shown on the right. The plotted number here is delta R short W. This is the difference in low cloud radiative effect between the first half of the time series and the second half of the time series. The black line is the observed value, and the leftmost red data point is the prediction from the cloud controlling factor method, which you see agrees pretty well with, or very well with, the observations. A second case we looked at is volcanic eruptions of Kilauea volcano in Hawaii. So in this case, the inset map on the bottom shows in a dot the volcano location, and then the box is the area that we studied downwind of the volcano. And the plot on the bottom left is a time series of sulfate emissions in that box, or sulfate concentrations in that box, where the seasonal cycle and trend have both been removed. And in this case, you see two spikes in the time series. These correspond to volcanic eruptions. And what we did in this case is we removed data from the eruption periods from the training data set of the regression models, then did all of the regression analysis with the remaining data, and then validated the method based on how well it could predict the cloud radiative anomalies during the eruption periods when the model was given the cloud controlling factor anomalies during those periods. So the result is on the bottom right. The black line is the observed cloud radiative effect anomaly during the eruption periods. And the leftmost data point is the prediction from the regression analysis, which again agrees well with the observations. So these test cases are giving us some confidence that the regression method can predict cloud radiative effect anomalies in cases where we know the direction of causality is from sulfur emissions to cloud response. So I think this justifies using the method for estimating ERF ACI. The final step of the analysis is to make an estimate of ERF ACI. To do this, we multiply the regression coefficients that we get from our analysis, which relate net low cloud radiative effect to local sulfate anomalies. We multiply those by the change in sulfate concentration between 1850 and 2014, which we get from CMIP6 historical runs. We do this at every grid point and then spatially average over the ocean. And then because our method isn't really set up yet to work over land or in polar regions, we had to extrapolate a little bit to get a global estimate. We do this by multiplying our ocean estimate by a scalar gamma, which is defined as the ratio of global ERF ACI to ocean ERF ACI, which we get from CMIP6 simulations. And so we do need to bring in GCMs here. So it's possible that our estimates are affected by model bias, either from imperfections in the estimates of sulfur emissions or imperfections related to how the models treat sulfate processing by clouds. But with that being said, I think the CMIP6 data are kind of the best sources we have for these red terms in the equations, and so we decided to use them in our analysis. And we also incorporated intermodal spread in the delta log 10s and gamma terms in our uncertainty estimates. Okay, the final result is here. This plot shows our estimate of global ERF ACI. Our estimate is on the bottom. The IPCC AR6 observation-based estimate is in the middle, and the Bello et al. 2020 World Climate Research Program assessment is on the top. And so you can see our estimate lies inside the proposed ranges from the other two community assessments, but our confidence interval is a bit narrower, and what's most different is that the upper bound of our estimate is more negative than the upper bound of the other two assessments. So in particular, values of ERF ACI between 0 and minus 0.4 watts per meter squared or so are possible under the WCRP and IPCC assessments, but those are implausible according to our analysis. And finally, we want to look at the implications for ECS. So we use the Bayesian method of estimating ECS developed by Sherwood et al. And we ran the calculation, but put in our estimate of ERF ACI in place of the original assessed range. And the result is shown on the right. We found that when we use our estimate of ERF ACI, we get a higher range of ECS values. The likely 66% range shifted by half a degree. So the main takeaway findings from our work compared to IPCC AR6 and the most recent World Climate Research Program assessments, our analysis suggests that ERF ACI is less uncertain and potentially larger in magnitude, and also ECS is larger. And the reference for our work is at the bottom. It's published in PNAS. So yeah, I would thank you for your attention and happy to take any questions.
Yeah, thanks so much, Casey, for a great talk. We have time maybe just for one quick question. Rob Wood asked, How much additional skill does the addition of SO4 add to the meteorological CCFs?
Yeah, good question. I mean, it's less than 10%. I forgot the exact number. The total explained variance is like 45% with SO4 and all the meteorology, and I can't remember exactly the number with only the meteorological terms. So I'll have to follow up with you on that, Rob.
Okay, great. Yeah, we're running a little low on time, but there's lots of questions in the chat, Casey. So yeah, please answer there.
Thank you, Casey. That was a great talk. Our final speaker for today will be Shang-Ping Xie. Professor Xie is the Roger Revelle Chair in Environmental Science at the Scripps Institute of Oceanography. Today he'll be talking about the joint low cloud WES feedback as a conduit to tropical SST patterns. And looks like excellent. Whenever you're ready. Thank you.
Okay, so this is a good. Okay, thank you for the invitation to speak here. So Casey's talk really sets the stage for my talk. So the main point today I want to talk about is the low subtropical low cloud feedback. Is oftentimes people tend to view that as a vertical one-dimensional problem. Has to do with the inversion, turbulence, cloud top cooling, and so on. But the results of my talk kind of indicate low cloud feedback is intrinsically dynamical, involving atmosphere circulation changes. So this is a collection of work done by my students and collaborators. So I'm just my talk is just represents that work. Okay. Yeah. So pointer. Okay. So this is a figure I took from IPCC AR6, showing the cloud feedback kind of in three different assessments. So overall, since AR5, the cloud feedback globally is considered to be positive, but still kind of suffering a large uncertainty. So that is why a lot of people, including many in this audience, are interested in cloud feedback. Okay. So this is an assessment of the global climate feedback. So the kind of a target is the global mean surface temperature. But when we take a look of the cloud distribution, especially low cloud distribution, and by the way, the uncertainty in the global cloud feedback stems mostly from low clouds. So that's the result also reported in AR6 and early literature. So
Did Shang-Ping's internet go?
Oh, no, but he's back. Shang-Ping, now you're muted. I think we need to maybe make him a co-host again.
Yeah.
No worries, no worries. Internet hiccup.
Is this still good?
I think it says you started screen sharing, but it hasn't loaded the image yet. Maybe.
Oh, it just happened again. Sorry.
No worries.
Yeah. So this is have kind of happened before. Yeah, I don't know. This has Yeah, so it just
Can maybe try stop sharing and starting again.
Should we maybe do a question for some of the questions for the previous speakers while we work out?
Yeah, that's a good idea.
Oh, wait, there we go. Sorry, everyone, hang tight. Okay, we can't currently hear.
yeah.
Oh, there we
see
go.
my screen, this slide.
Now it works. It's great. We can see it and we can hear you. Excellent.
Okay. Okay, sorry for this.
No worries, no worries.
My Zoom. I don't know. I simplified. Anyway, so let me run through this quickly. Just yeah. So I'm sorry for the technical.
No worries. No worries.
Yeah, just the subtropical low cloud deck are concentrated in the Eastern Ocean. So you know, this distribution would kind of tell us when the low clouds, subtropical low clouds varies in response to internal variability or radiative induced climate change. The cloud radiative effect is going to be localized, and therefore as a thermodynamic driver for atmosphere circulation, and therefore SST, and it's going to trigger a sweet dynamical adjustment in both the atmosphere and the ocean. So that potentially can lead to SST patterns, rainfall patterns, and so on. And therefore has, in other words, you know, the pattern effect that we have been discussed in the literature recently could you know, be traced back to this localized nature of low cloud distribution and feedback. So that is the main point. Anyway, so this is a chronological distribution of low cloud occurrence seen from ships. So we can see kind of in northern hemisphere summer, just southwest of California, we have a cloud cover of 80% or more. And then the tree, you know, the subtropical high kind of circulating like this, and then the green contours are the sea surface temperature contours. So you can see there's a strong cross isotherm advection, people call cold advection. So that's considered to be important source of boundary layer turbulence, and therefore a low cloud contributing to the maintenance of a low cloud cover. So you know, looking at this sea surface temperature contour, you can see this kind of deep south, right? Kind of indicating there's a cooling effect by the low clouds. So for a long time, I kind of wonder, you know, how much you know, this low cloud deck can cause this local cooling, you know, in terms of magnitude. And then there's a study actually led by Miyamoto, Ayumi Miyamoto. So who, by the way, is just going to join Scripps Institute of Oceanography as postdoc starting today. So actually, incidentally. So he did a nice study by disabling the cloud radiative effect in a couple ocean atmosphere model, which is the CM 2.10 model, but still kind of very useful. At least they can run very fast. So anyway, so he disabled the cloud radiative effect in this box, and then he saw a change in the sea surface temperature underneath, right? So in other words, the plot is made so the SST change is negative. So this represents the cloud radiative effect in this box on the Pacific or even the global the climate system. So anyway, so in other words, this experiment showed the cloud radiative effect in this model can lead to a cooling of 3 degrees or more Celsius in this low cloud deck region, and then this localized cooling would induce an anticyclonic circulation in the atmosphere boundary, and then the anticyclonic circulation. The southern flank, the winds are strengthening the northeast trade winds, and therefore intensifying surface evaporation, and therefore causing the cooling effect to extend southwestward, right? And this is what I meant. You know, a localized feedback can trigger a large-scale atmospheric circulation, causing the SST to cool. And the further cooling outside this box can further induce or enhance anticyclonic circulation to the southwest because the Rossby wave dynamics, right? So the Rossby waves propagate westward, and then the zonal phase difference will cause the initial cooling to propagate southwestward. And eventually, as we will see in a minute, reach the equator and imprinting on the sea surface temperature, kicking off Bjelken's feedback and so on. So this is, I think, a kind of a nice study to quantify how much the local cooling is, and how the local cooling can induce a couple of waves, basically, propagating toward the western equatorial Pacific. So this is a kind of model experiment, right? So we also wonder whether we can see the same like joint low cloud and the wind evaporation SST feedback in observations. So in observations, we have a lot of satellite data since the 1980s and so on. So we kind of take the sea surface temperature anomalies in northern hemisphere summer, JJA, and then use this area averaged SST variations to calculate the correlation and regression of SST in color shading and the surface winds in arrows, and the cloud radiative effect on shore wave in green contours. So in other words, when the sea surface temperature in this box is anomalously warm, it induces a cyclonic circulation in the atmosphere boundary, and on the southern flank of the cyclonic circulation, the trade winds are reduced, and then the reduced trade winds kind of cause the sea surface temperature rise. So that again, we see this a nice southwestward propagation out of.
Shang-Ping, I think we might be behind a slide in terms of what we can see.
Really?
Unfortunately.
Okay, maybe I push another one.
I apologize. Sorry about this.
Does it forward? Does it go
Maybe
forward at all?
It's staying on the same slide, unfortunately.
Oh, okay. It doesn't move?
No, we're still on the third slide.
Okay, I'll resharing. Okay. Yeah, it's somehow, does it? Oh, okay.
Oh, I think
The unmute.
there we go.
Yeah. Okay. Sorry.
Yeah, maybe if this keeps being a well, there they are.
Oh, so I could send. Yeah, maybe it's a little too late.
Yeah, it's okay. We can make them
Yeah,
available
somehow
potentially if you'd like.
it's sending. Yeah.
We can run a little bit late as well. Do you want to keep
Yeah,
going like this, Shang-Ping?
Looks like
I cannot.
oh,
Okay, so somehow I cannot sharing.
We're seeing your PowerPoint, Shang-Ping. Maybe we could just use
Oh, really?
that. Yeah.
we could potentially take a moment. I know we're getting towards the end of the hour. Shang-Ping, if you wanted to send me the slides as a PDF,
Okay,
and
I will do that.
I could advance. And maybe while you do that, we can, if there are questions for
that's a good idea. Yeah.
previous speakers that people wanted to ask before the end of the hour. But otherwise, we'll be here. You know, I'll stick around. I'm definitely want to stick around.
Casey, are you still around?
Yeah, I'm still here. I'm still here.
Okay. Maybe I'll ask a quick question from the chat. I see Claire Singer asked, it seems like your ERF ACI estimate is more certain, i.e. narrower, but the ECS estimate has not narrowed. Why is that?
Yeah, that's a great question. I think the reason may be that I'm thinking of Gerard Rowe's work showing that if you have the same absolute uncertainty and feedback or forcing, but kind of shift the range such that the central estimate of ECS gets larger, that will translate into a larger uncertainty range for ECS. The same uncertainty and feedback and forcing can translate into a larger uncertainty in ECS, just because the nonlinear relationship between ECS and feedback. So I think that's a possible explanation. Yeah.
Okay, and then Lazarus Oriopoulos asks, is it possible that the MERA2 910 HPA sulfate concentration has biases that depend on cloud fraction?
Yeah, that's a really good question, really hard to address directly. One thing, kind of the best check that I could think to do was to repeat the analysis with MODIS cloud droplet number concentration, thinking of that as a proxy for CCN. And that's kind of an independent proxy because the ND data come from the cloudy pixels. The MERA2 is constrained on the AOD from clear sky pixels. And so I did get consistent results with both of those. So that kind of gave me some confidence. And I also know that MERA uses a strict kind of filtering procedure for trying to remove clear pixels that may be contaminated from clouds. So I don't know if we can totally rule out biases, but I guess I felt the consistency with the ND data was promising.
Okay,
great. I think we have the slides up.
Yeah, so I'm just going to quickly kind of Yeah, so this is based on observational interannual variability. We see kind of this when SST in the box is warmer, then this induce a couple of mode, we call it Pacific meridional mode, basically, kind of due to the circulation and SST adjustment. So this the southwest propagating meridional mode showed up in the interannual variability observation. And then can we go forward? Yeah, and this compared to Ayumu Miyamoto's model experiment when he suppressed the cloud radiative effect in this box. You just compare, you know, the remarkable resemblance between the model simulated meridional mode induced by the cloud radiative effect in this box. Of course, this based upon artificial suppression of cloud radiative effect, whereas this is induced by this reflects the observed interannual variability. So, but just, yeah, remarkable. I just was amazed. And then, can we go forward? Yeah, and this observation, you know, just to show this observed meridional mode propagate southwestward, eventually reaching the equatorial Pacific and leading to a development of El Nino on the equator. And then, can we go next one? Yeah, and this is a CESM simulation, a sim analysis. You just see, you know, very remarkably similar. And then the next one. And this is when the CESM cloud is locked, right? So prescribed cloud. And you see this mode, but very weak, and therefore it's insufficient to trigger any changes in the equatorial Pacific. And maybe we can just skip all the way. Yeah, maybe all the way, yeah. Yeah. Oh, yeah, maybe I will end with this. So one back. Sorry. Yeah. Okay. So this is a simulation done by Matt Longo, a graduate student at the Scripps. So he used the CESM to investigate the climatic response to an extratropical northern hemisphere radiative cooling, and that leads to certain patterns. And we saw this PMM-like joint low cloud west feedback mode. And importantly, he finds the equatorial Pacific response. You know, when you cool the northern hemisphere, a La Nina-like pattern showed up in the equatorial Pacific, and that the strength of that pattern in Matt's analysis, multi-model analysis based on AtomMip, show kind of we identified a linear relationship between the short wave cloud radiative effect in the northeastern Pacific in the low cloud deck region I was just discussing, and the equatorial Walker circulation strength, or the east-west temperature gradient on the equator. So you kind of see this multi-model dots kind of identify CESM as outlier in terms of maybe very strong low cloud radiative effect. So a lot of people would think that this is a bad thing for CESM because nobody wants to be outlier. But again, you know, when we analyze the interannual variability from the observation and from the CESM long control simulation, we actually find, you know, the correlation and the regression slope from the CESM are very similar to observations. So in other words, the outlier behavior, strong as low cloud feedback in the CESM turns out to be quite realistic for some reason. Yeah, so in other words, you know, the observed interannual variability could be used as test bed metric to calibrate, to kind of to measure the model subtropical low cloud feedback. You know, yeah, the slope. So that is a little point. And maybe, yeah, so yeah, the next one. Yeah, so this is basically, I want to say low cloud decks are localized, and therefore low cloud feedback intrinsically is coupled with the wind evaporation SST feedback, leading to a southwest, the west equator-ward propagation of any anomalies in the variability or change in the low cloud deck region. And then low cloud being a positive feedback tells us that low cloud feedback is also a very effective amplifier and a conduit to tropical SST patterns. And we have seen this in various different contexts. I don't have time to go into to show those examples. But if you pay attention to the patterns in the radiative induced climate change, I bet you're going to see this joint low cloud west feedback very often, simply because it's powerful amplifier, not only for the global climate response, but also very kind of obvious and pronounced in the spatial pattern extending from the low cloud deck region toward the equatorial oceans. I'll stop here. I apologize again for the technical difficulties.
No worries. Thanks so much, Shang-Ping. Really interesting and kind of provocative talk. I want to ask a question, something I've asked Matt a lot about, but do you think this means that we need to be careful about using fixed SST simulations to study cloud feedbacks?
Yeah, so I think we need to reflect a little bit, just because the equatorial SST patterns could originate, at least be part of an interaction between the subtropical climate and equatorial and the tropical climate. So these are actually two-way interactions now. And this kind of the change in the thinking also happened in the studies of El Nino Southern Oscillation. So when people first studied ENSO, because ENSO's tight connection to exotropics, but now we realize the very behavior of ENSO can be traced back to the exotropical variability via this west PMM low cloud coupled wave pathway or conduit.
Great, thanks. If you're okay with it, can we stick around for a few minutes in case anyone else has questions for Shang-Ping or also for Casey? I'll ask another question of Casey from Gita, which was, how much does the spread in gamma from CMIP6 contribute to the confidence interval on the ERF estimates?
Yeah, it's like cool. All of the three. So we have uncertainty from this gamma term, which is basically the contrast between ERF ACI over ocean versus the rest of the globe. We have uncertainty from the pre-industrial to present day change in sulfate concentration, and then uncertainty from the regression slopes relating cloud radiative effects to sulfate concentration, and they're all like contributing comparable amounts to the overall uncertainty.
Great, thanks. Any more questions, especially for Shang-Ping? Oh, Paquita, do you want to unmute?
Yeah, I have one for Casey, if that's okay. I was wondering if you, how you separated out the sulfate from other aerosols that might be contributing.
Yeah, that's a good question. I've tried to do this, but I was getting results when I put in a bunch of different aerosol species. I was getting results that didn't, sorry, concentrations of a bunch of different aerosol species as predictors. I was getting results that seemed kind of possibly unphysical, because I think when the clouds start precipitating, they remove all of the aerosol species together. So if you try to constrain like sea salt, black carbon, etc., concentrations, you can't really get the precipitation effect on sulfate without, if you're controlling for all of those other species. So we can't totally separate that out, but we do control for wind speed, surface wind speed in our analysis, which is what determines the flux of sea salt or the emission of sea salt aerosol. So I think that's pretty well controlled for, but yeah, it's a good point that we can't, if there's co-emission of other species that are acting as CCN, we can't really tease those apart. So that's a potential source of bias.
Thanks, that's helpful.
Does anyone else have questions? Just trying to get to about 50% the audience. Not, thanks again so much to the speakers for a really great session. And yeah, we'll see everyone next month.
Thank you, everyone.
Hey, Nick, I'm just going to copy all these questions in the chat so I can follow up.
Yeah, we normally put the chat on the website, so you'll be able to see it.
Oh, okay, awesome. I think maybe there's some message just sent to me though, so I want to try to grab those.
You probably want those, yeah.
Thanks to the organizers and bye.
Only getting information about who sent the message. I might try to copy it. Okay. Okay, cool. I got it, Nick.
Okay, great. And thanks again for presenting.
Yeah, thanks very much for organizing. That was great.
All right, see you guys.
Yeah.